Okay, should I just start? Okay, yeah. So, right, so first of all, hi everybody. Thanks for the organizers for putting on this this interesting workshop. And so, yeah, I'm obviously kind of the odd one out in terms of topic. And I have 3 lectures, and I thought that the first one today, I will talk very broadly, try to give some context, and also not really spend too much time on the technical details, and where the technical details are important, I think, to make contact with issues of quantum statistical mechanics and quantum chaos. I will use the next 2 lectures to go and supply more of those mathematical details. But now also today, maybe we should be sure also that we sort of touch base and that we're on the same page. So you should really feel encouraged to ask questions. And that will probably also help me to gauge a little bit more what to say in more detail and maybe what to skip, okay, for the next 2 lectures. So, so the title of my series of lectures is Quantum Chaos, Quantum Gravity. And certainly, at least one of these is sort of a very ambitious topic. And I will try to, keep this to the confines where it is actually more or less well defined. But to go there, I will need to give you some background that, as I said, is maybe a little bit more hand-wavy, but hopefully helpful to see where we want to go. So the first lecture basically is supposed to tell you, and I'm trying to tell you why we can think of black holes in several ways as chaotic systems. So today I will talk about black holes as chaotic systems. And so obviously we will have to spend some time on thinking about what are black holes in the first place. So let me start with that. So the prelude is, so first of all, I'm going to tell you about the entropy of black holes. Then I'm going to tell you what that tells us about the supposed Hilbert space of black holes if we think of them as quantum systems. I will then introduce, in some sense, the complex of questions that at least myself and some others study when we try to quantize these objects. And I will then finally make this connection to chaos, and in particular in a framework to think about quantum gravity that's called holographic dualities. And then, as I said, maybe the next lecture, if you want, I can go more into what are these holographic dualities, and then use the last lecture to talk about what chaos has taught us in recent years. If it turns out that most of you are familiar, I can go more into the meat of what has happened in recent years already in the second lecture. But give me the feedback, and we'll see where we go. So the statement to be established is that black holes have entropy. Okay. And I'm going to write down the formula, which I'm sure you have all seen. It's this famous Bekenstein-Hawking formula that if you have such a black hole and under very generic circumstances, we can think of these black holes actually as sort of the point masses and a surrounding sphere. Then I associate an entropy which is actually proportional to the area of the sphere divided by 4 times the Newton constant. And I'm going to work in units where I said h bar is equal to c is equal to Boltzmann is equal to 1. Okay, so this is this celebrated Bekenstein and Hawking formula. For the entropy of a black hole. Okay. Yes, so the area is a function of the physical parameters of the black hole, which is like its mass. Okay, it could also be rotating. Let's not do that. But the mass is basically determined is determined by the radius of the black hole, the Schwarzschild. So the Schwarzschild radius is a dimensional parameter that characterizes the simplest black hole that you can imagine. It determines via actually an integral formula its mass, and this area depends on that. So we could write down explicit formulae, but I don't want to do that right now because I will write down some more explicit formulae later on, let's say. But in principle, of course, it's the area is determined in terms of how big is this black hole, and how big is this black hole is essentially the mass energy that's contained within the black hole. Very. So, how do we actually arrive at such an entropy formula? So this is, of course, just a statement that I'm making, and Wittgenstein proposed it, I believe, in the 60s, and he made some qualitative arguments that used thermodynamics and so on, and he was able to argue for the area. My understanding is that this factor of 1/4 was a complete fluke. He guessed it, and he guessed it correctly, so maybe it wasn't a complete fluke after all. But to really determine it was sort of the work of Hawking and people around Hawking. And so what they were doing was actually, let us try the following thing. Let us try to think about gravity, gravity semi-classics. So what do I mean by this? Well, first of all, of course, gravity as a classical theory is something that we understand to be general relativity, or Einstein's geometric theory, so Einstein's theory. Okay, so this is the classical theory, and that has an action. We know that S, the Einstein-Hilbert action, EH. Okay, this is the action principle which determines all the classical solutions of Einstein's equations. We like to think about it in these space-time dimensions. Of course, we live in 3+1. So D is the space-time dimensionality. Okay, so then you have the curvature density. Let me just say this is the determinant of the metric. You have some geometric terms, and then let me tell you exactly what I mean here. So G mu is the metric, and mu are these indices. So mu actually run from 0, 1 to b minus 1, right? So there are d directions, this, and the rest will be space. G mu is the metric, and then G is the determinant of this metric as a d by d matrix, and then these are geometric curvature quantities. So at this point, maybe ask, because it's important. How many of you are actually more or less familiar with general relativity and how to think about this as a classical theory? Best to be honest at this point. Okay, yeah, but that's kind of what I assumed. So there is, however, not enough time to really obviously give a course on GR, but let me still give you some notions. Actually, I think I might have got these notions a little bit later. That's right. I'm giving you the notions. I'll be giving you some more notions of what these symbols mean in the next section. First, I wanted to just say, how does a classical theory semi-classically give an entropy? So for this, I forgot to write, there is, of course, a factor here, which tells us, in fact, what is this Newton constant that I talked about before. I mean, you're familiar with Newton's constant, of course, from things that fall, but here it is basically the dimensional coupling constant of this action as a classical theory. Okay, but what Hawking and friends did, they were saying, we can think of this, we expand. So we think of this as a semi-classical theory. So we expand this around classical actions, expand around classical solutions. In small g Newton. Okay. So I should think of the metric, the field g mu to be something that's like g mu, which is a classical solution. Plus a small perturbation, which actually people like to normalize with the square root of this times h mu. So this is a classical solution, and this is a small deviation. And then what people do is they literally close their eyes and they say, let's plug this guy in here, and let's try and think of the resulting theory of the h mu as a quantum theory. Okay. This actually doesn't work. I should be quite honest about this. This actually doesn't work, but it works as some approximation. So this small deviation. So yeah. Well, yes. So the idea is simply the following: is that if so, to answer that question, I sort of have to pretend a little bit more here, which is that so you take this theory and you say that you can define a path integral over the fundamental fields S Einstein-Hilbert, and actually, yeah, dg Einstein-Hilbert, which is a functional of the metric. Okay. The problem is, I'm just saying this to answer your question. The problem is that this object isn't really well defined, and why it isn't really well defined is this famous statement that gravity, is not UV complete. There are UV problems of this theory. It's a non-renormalizable quantum field theory that we don't know how to cure. So this path integral isn't really well defined. But what people do is, that's what I meant by they close their eyes. They write this and they think of maybe imposing some UV cutoff. Okay. So they say that we should think of this only as an effective field theory, which is valid as a quantum theory at low energies. Okay. Does that make more or less sense? Now, to answer your question, then they say, okay, let us try a background field or a semi-classical quantization of this object, where we say that we stick this thing here into the action, where G bar is a solution to the equation B2S Einstein-Hilbert E2 G mu evaluated on G is this G classical is equal to 0. Okay, so solve the classical equations. Sorry, d s p g mu is equal to 0. Okay, but then you expanded around this classical solution in small fluctuations, and you literally quantize in h mu, okay, the fluctuations. It is exactly that. It's like so one way of saying it is what I'm talking about, what I call semi-classical gravity. Is the same as saddle point approximation times the one loop fluctuation around it of h, right? And the one loop fluctuation is the determinant precisely of this operator that I wrote before. So we can write this as the determinant of d2s by dg2, the fluctuation around the saddle point. Okay. But I'm getting in far more detail right now already than what I wanted to do. So we can go on like this and I just respond to questions, but I think I might be going too much into the weeds already. But there was another question nevertheless. Physically. No, this is another good question. So now, in order to answer this question, we need to think about, first of all, what does this mean? So, as no doubt you have heard, but maybe not in detail, the solutions to Einstein's equations are supposed to determine space and time. For example, the space and time that we live in, like the classical solution. They're of course analogous to classical field solutions of other theories like electrodynamics. Okay? So it's like having a classical solution to the Maxwell equations, but here the dynamical field is what determines the macroscopic properties of our universe, let's say. I'm saying let's say because that's one of the solutions that's allowed. There are other solutions which are not our universe. They're mathematically also allowed. Now, these solutions you can think of as being the background on which physics happens. Like they literally are the background of the universe. And physics that's happening here, that's determined by this Gn, is small fluctuations, which you know as gravitational waves. And if you go to the quantum regime, those become what we call gravitons. And Gn will be the interaction between gravitons. So how does that work? Let me tell you that. This thing here is a nonlinear function. It's a highly nonlinear function of G. Okay. So it can actually be expanded as a power series in H. And this power series will generate diagrams of the kind where you have like one graviton that comes in and it scatters into, for example, two gravitons. And this will be, you know, G Newton, but it also generates all kind of higher order terms. But let me just say that if you did this to Maxwell theory, if you did this expansion to Maxwell theory is a quadratic theory, you would find no interactions between photons. The ripples of the Maxwell field, the photons, they don't interact. The classical ripples of the gravitational field, they do interact. And square root of G Newton is the strength of the interaction. So G Newton, and actually in this context, square root of G Newton is the coupling of length. Okay. Does that make some sense? Now, if you know this, of course, if you actually quantize the Maxwell field, then because of virtual interactions, you can have photons that interact, but that's a quantum process. In general relativity, the classical theory is already highly nonlinear, so the fluctuations actually interact. Okay, and the interaction strength is G Newton. So that means that the small G Newton expansion is an expansion in weak coupling of the gravitational interaction. It is, but it's not, I didn't write it in coordinate independent way. Interesting question. I don't think that's right. And when I was a graduate student, we had a sort of a very mathematical GR course, and the professor spent like 4 weeks on this statement, and we all thought it was ridiculous. He spent 4 weeks. So he showed under which conditions you can define gauge invariantly the smallness of the interaction. I did not show you how to do this, but it can be done. No, the thing is that you need to define what is the perturbation itself in a gauge invariant way. And then you have a set of gauge invariant physical perturbations, and it makes sense to speak of them as being small. But those are kind of very subtle issues, which really we should not talk too much about. So, okay, well, this looks far more detailed than what I was going to say. Where were we? Okay. So semi-classical gravity is something that is really sort of a technically accepted term in our community. And what we mean is this story, the following, is that we close our eyes, we pretend that there exists a path integral over the metric. Exists not in the sense that mathematically path integrals are complicated, but even physics-wise, this theory is not a good theory in the UV. It's not a normalizable quantum field theory. But we can think of it with an implicit cutoff as an effective field theory at low energies. And then this actually makes sense. For example, at one loop order, this can be made to make sense rigorously. And at one loop order, then, one can just do a saddle point approximation where we expand around a given classical solution of the equations. So then this saddle point, of course, gives me e to the minus s evaluated on the saddle point, literally. S of g hat, and then I do the fluctuation determinant as a quantum object around the saddle point, and that is this formula here, the functional determinant of the fluctuation operator evaluated at the classical solution. And this expression here, that is what I call the leading semi-classical approximation of the theory of gravity. Okay. Within this complex of objects, I can make sense of the Wittgenstein-Hawking entropy, and that's actually what I wanted to talk about. Yeah. The cutoff does not enter the entropy at leading order, but corrections will be cut off dependent. And the reason why it doesn't actually enter the entropy at leading order is that you can actually absorb it into a renormalization of Newton's constant here. Yeah. Yes. Yeah, that's a great question. So I think I will answer that question in the next 2 lectures. But for now, here, actually, there are very few saddle points. And the fact that there are very few saddle points is actually the subject of theorems, such as what is called the black hole uniqueness theorem, or people call it the black hole no-hair theorem, which were proven again by Penrose, Hawking, Bardeen, Carter, people like that. And they say that under realistic assumptions, meaning we live in 4 space-time dimensions and we live in a space that is, well, I don't know if that's related, by the way, but we live in flat space. I think we live in de Sitter space probably. No? But let's say we live in flat space. Then there is actually a very small number of static spherically symmetric solutions of Einstein's equations, and they're basically all the known black holes. This, by the way, this is complete deviation now, but this is literally the reason why these gravitational wave observations work, and that's also the reason why Penrose was justified in receiving a Nobel Prize for a mathematical theorem, because there are so few solutions of general relativity that are compatible with the observations that you could with certainty say that the signature has to be related to a black hole, and not one of, you know, a gazillion other possible saddle point solutions that we could have seen. But those literally in like flat 4-dimensional general relativity, that's a theory that's extremely well defined, unlike this theory, and where statements such as black hole uniqueness and how many saddle points and so on can be actually proven at the rigor, mathematically rigorously in analysis of PDE type sense. But we will need to find somehow a role for many saddle points and interference between them once I want to talk about semi-classical chaos as well. But that's okay, that's not for today. Good. So, right, let me see what I actually wanted to say about this. Well, yeah. So there's no something that is really quite strange, apart from the fact that maybe for some of you this is unfamiliar mathematical or physical territory, but there is something also very strange because I already said that there is this analogy in some sense. I mean, the Einstein's theory of gravity is just a field theory. It's just a classical field theory. And yes, we can think about it as sort of a semi-classical system, but so is Maxwell theory. It's also a classical field theory. And nobody ever said that, you know, there is an entropy associated to its classical solutions, like the Coulomb field. No entropy associated to the Coulomb field as such. Right? So what is going on here? Okay. That's all right. That's all right. Now I just need to not slip. Okay. We also have one of these squidgies. Okay. So let me try and say it in words first. So that was essentially where Wittgenstein was coming from. So it is true that black holes are perfect absorbers, which is of course where the name comes from. And that's literally in the sense that anything that falls into a black hole can never come out. And so Wittgenstein essentially realized that if that is the case, and you drop something that's very entropic into a black hole, then you can decrease the entropy, because, you know, if there isn't an entropy associated to actually the black hole itself, then all this entropy will just disappear, will not be available anymore. So the black hole should have an entropy. Okay, so Wittgenstein argued that then we need to associate an entropy to a black hole in order to save the, let's say, to save the second law in the universe. Okay, but actually it can be much more rigorously shown that this is the case. And in fact, what can be shown is actually what can be shown is there exists classical theorems there exist there are properties of the classical Einstein equations which are perfectly analogous to the laws of thermodynamics. Namely, so the laws of black hole, people like to call it the laws of black hole mechanics, but people also sometimes call them the laws of black hole thermodynamics because they identify the two. And basically, the important one are something like, well, let's say a second law, which says that the change in area of the black hole in any physical process has to be strictly positive. So area, again, was the surface. This is this area, surface area of the black hole. This, for example, I think has been tested also in black hole mergers now through LIGO. So for example, if you have two black holes, you know, they have a sum of the two areas of the horizon, they fuse into one black hole. That's what's happening in these inspirals. You better make sure that the total area afterwards is bigger than the area before. And that is, at least according to the data, that's correct. There is also, well, let's say there is a first law, but the first law needs something else. The first law needs the so-called Hawking temperature. So actually, Hawking identified a temperature, TH, of a black hole, which actually turns out to be, in the simple context that we talked about, to be 1/8 pi times the mass. Okay, so with this, you basically can identify the temperature and the entropy of the black hole, and then the dynamical equations of GR imply a first law between that temperature and the entropy. So you have a first law if you say that there's a temperature of the black hole and the S of the black hole is equal to 1/4 times G Newton times the area. So this fixes the factor of 1/4. And in fact, there is even a zeroth law if you want. The zeroth law basically just says that in equilibrium, the temperature of the black hole, 1/8 pi times m, is constant across the horizon. So there also exists a zeroth law. And so these laws of black hole mechanics actually give us a good reason to think that we should interpret these as thermodynamic quantities. Okay, so yeah. That's the next step. No, but maybe you have a specific question, please go. Yeah. No, but that's right. So that's why also I actually called them, I prefer to call them the laws of black hole mechanics. This does not necessarily mean that there is any thermodynamic interpretation. It could just be a coincidence. It could be a complete coincidence. And so that is, and this is what I wanted to actually say in the first half of the lecture, no, first third of the lecture today. So I'm not doing so badly. I wanted to basically define through this what I call the program of quantum gravity. And the program of quantum gravity, if you want, is to actually give this a meaning. And to give this a meaning, at least from my point of view, and I think other researchers share that also, in a statistical thermodynamic sense. Okay, so if we accept this, I mean, we accept this because it's true in the sense of, again, literally mathematical theorems, because it's a statement about classical solutions of Einstein's equation. But we don't need to necessarily interpret them as thermodynamic laws. But if we want to interpret them as thermodynamic laws, we better find a statistical physics interpretation. And the statistical physics interpretation of this involves what I refer to as the black hole Hilbert space. Okay, so let me say that now in a few more words. Actually, I'm sorry, I mean, I had some more details about what a black hole actually is. So I think I will tell you this as well. Okay, but maybe I will first, because I think it's a natural flow of ideas, I will first talk about this black hole Hilbert space, and then I will go back and say a little bit more. What is a black hole? What actually is a horizon? If I make statements like the temperature is constant over the horizon, what do I actually mean? Okay, so I'm inverting a little bit flow, but I think it's Jorge is right that this is a very natural thing. So what we want, therefore, okay, we want an interpretation kind where S black hole is the logarithm of a number omega of microstates. So omega log omega is, so in other words, we want a statistical entropy in terms of black hole microstates. So in other words, we actually want a quantum statistical interpretation of some classical properties of the Einstein equations. And this is, at least to my understanding, maybe experts in the audience can say otherwise, that's still a somewhat peculiar situation where somehow the classical theory in itself carries some hints that there is actually an underlying statistical description. As I said, this is certainly not the same. I just want to emphasize this again. This is not the same in like electrodynamics. You know, there is no need to have like a surface around an electron that carries entropy that, for example, proportional to its surface area. There is certainly no first law I can write down that it's to do with the classic exclusion of the Coulomb field, etc. So in general relativity, the classical theory has properties which are perfectly compatible with the three laws of thermodynamics. And it somehow seems to tell us that there are underlying microstates whose entropy we can associate in a microeconomic by Boltzmann to this entropy. And that means that there should be some quantization. So let me write it here maybe then. So this is like the one way of thinking about the goal of quantum gravity. Is to define the black hole Hilbert space such that the dimension, obviously, of the black hole Hilbert space is equal to E to the classical entropy of Bekenstein and Hawking, okay? Which, and I want to make this statement already now, is a finite quantity, under very general assumptions. Again, because under very general assumptions, the horizons of black holes are compact. They have a finite surface area. And the finiteness of this black hole Hilbert space will be quite interesting when we start talking about quantum chaos, because this, for example, has to do with the fact that you can see ergodic signatures and so on, because you will have actually a discrete set of microstates and you can start to see interferences. Okay, so this is one of the goals of quantum gravity, is to define what is black hole Hilbert space. But of course, you also want to do a little bit better. You will maybe want to understand the dynamics. And by this, I mean, you want to actually know more about the spectrum, like how are these microstates actually ordered and how can we think about them dynamical quantities. And this second aspect here, this is something where in recent years, we have, I think, made quite a lot of interesting progress in using insights from quantum chaos. But that's, again, will be toward the end of my lectures. Okay, but so maybe the minimal goal is to define the microstates and count them, and then find out that actually they are the microstates that account exactly for the Bekenstein-Hawking entropy numerically, quantitatively, and therefore we can use all of our understanding of quantum statistical physics to really interpret these laws as thermodynamic laws. Yeah. Yes, but of course, you want to understand the entropy, the macroscopic entropy of any object in terms of the underlying microstates in a quantum statistical sense. The entropy is fixed. That was the for example, the mass of the black hole. Of course, you know, this is the same as the energy, and that fixes the energy. Yeah, but you know, of course, you can think about classical statistical mechanics, but ultimately, this is always a classic limit of a quantum system, and so, you know, the actual microstates that underlie the system are supposed to be quantum mechanical microstates, and that's also the case here. Yeah. So. Yeah. If you want, I can maybe next time I can actually give you a derivation of the entropy of a black hole. Maybe that would be useful. I was hoping, well, not hoping, I was planning not to go into it because it needs, you know, manipulations of the metric and so on, which I assume that maybe the audience isn't too familiar with. But if that's helpful, I could do that, and maybe then we can discuss that question more. Oh, sure. Yeah, we could. Yeah, that would be fine with me. Yeah, yeah. But right. Yeah, maybe to have a more substantial discussion about this question, it would be good to first go through that derivation. Yeah. Well, I mean, so the entropy comes from realizing again that it is mathematically consistent to think of this path integral as a thermodynamic potential. And this thermodynamic potential, it just falls out of this path integral. But what it doesn't characterize is what actually are the microstates that account for the entropy. It's just a formal definition. No, it's not. No, it's not. And actually, well, this can be made much more precise in the context of holographic dualities, which is where I'm going to head to in the next lectures. And there, in fact, you can think about the difference between what people call the graviton fluctuations. You can actually sum them up completely. And you can show that they give like a sub-extensive contribution to the entropy. It's not that their entropy is zero, but in this context, by the way, I could also tell you that they will give you like a logarithmic correction to the classical formula. So you get the classical formula and you find a logarithmic contribution that is subleading to the Bekenstein-Hawking entropy that comes from the fluctuations of gravitons. Okay, but again, this is at least somewhat of a technical discussion. Other questions? Okay, so let's see. Right, still some time. Yeah. So maybe maybe the best thing to do is to still go through this somewhat more intuitive picture of what actually is a black hole, that allows me to define what is a horizon. I've already talked about the horizon. I think it's quite important to at least define it, and even at an intuitive level. And then I guess we'll pick it up either in some afternoon discussion or in the next lecture. I wanted to finally end up making some connection to these so-called graphic dualities because they fit quite nicely into this complex of topics of the laws of black hole thermodynamics. But yes, let's just take the time and not rush. Okay. Does this actually ever work, by the way, without making a mess? No, I think not. Yeah, no. Actually, no, it's not. I think it's okay if I. Okay. Are there other questions in the meantime? Yeah, go ahead. Yeah. Good. Why do I focus so much on black holes? I mean, there's many answers to this question, but one is they're at the same time the simplest objects you can think about. Also objects that actually are very useful because they lead you very quickly to the limitations of our current understanding. But if you want maybe the best answer is that they are really the simplest objects that you can possibly account for. And so it's a good idea to try and understand those extremely simple objects first. Like understanding, for example, cosmological solutions, like, I don't know, asymptotically de Sitter space or things like that, is way more complicated. So it's maybe a slightly more modest goal even. But on the other hand, these laws of black hole mechanics are extremely intriguing, and a great number of people believe that they somehow hold the key really to understanding what's going on at the quantum level, and they come from black holes. Okay, so so what is a black hole? So I already wrote the Einstein-Hilbert action. I did want to write the actual Einstein equation. So first of all, they are solutions to the Einstein equation, which is of the form, let me just write it first, r mu nu minus 1/2 r g mu nu is equal to 8 pi times g Newton times t mu nu. And so what do the terms here mean? Well, the left-hand side is the curvature of space-time. And the right-hand side is the energy and matter content. And so people often talk about this Einstein equation as saying that matter tells space-time how to curve, and actually the curvature of space-time tells matter how to move. So both of these aspects, dynamics and background, are encoded in these equations. But let's say a couple more words. So this, okay, just to define quantities, I should define them anyway. This is what is known as the Ricci tensor, and it's a contraction of the Riemann tensor. So this is a nice way in Riemannian geometry of encoding the fact that space-time can be curved. So we have a curved space-time, but actually it's not just the Ricci tensor that defines it. There is also the Ricci scalar. So R would be the contraction over all indices of this. So mu nu of r mu nu r mu nu. This is called the Ricci scalar. So the thing with two indices is the Ricci tensor. This is the Ricci scalar. And this combination people call the Einstein tensor, because obviously it was first written down by Einstein. And it's the thing which is the good way, the good combination of geometric quantities, that it gives exactly the response to putting matter into space-time. And so the point is that people always draw this picture, you know, like you have space-time, which is maybe a two-dimensional analog where you have some membrane. And if you plop a big object like a star in here, like this could be the sun. Actually, maybe I should be more abstract. Okay, so if you put like the sun in here, okay, then what this does, it kind of makes a dent in space-time, right? It sort of curves space-time, and it makes like a dent, and this dent deforms space-time and changes this geometric quantity. And this thing here is literally just the energy momentum tensor, as in any other covariant field theory. For example, in Maxwell theory, you also have an energy momentum tensor. The space components are the stress energy tensor. The time component is just the energy density. So this is energy and matter. However, what those things are, so I said solutions, okay? In actual fact, these are a set of nonlinear partial differential equations, plus, we should be honest, there is also some constraints, which is at least mathematically kind of annoying, but that's what we have. That's actually also what you get in Maxwell's equations. By the way, there are things like the Gauss law constraint. So there are something like a gravitational Gauss law constraint. And this set of linear PDE with the correct initial conditions has a set of solutions, and a black hole is just one of these solutions. But what is it actually? So the solution for a spherical point mass, black hole is a solution corresponding to a mass source, and it is spherically symmetric. Okay, this is one of the assumptions. Typically, it's spherically symmetric. Okay, now it's just sort of a homework which famously Schwarzschild actually performed while he served on front lines in the First World War. And he basically wrote down Einstein's equations like this. He assumed spherical symmetry around a point mass, and he was just asking, can I write down the solution for this fundamental degree of freedom G? I should, of course, have the Ricci scalar and the Ricci tensor both just depend on the metric G. So once somebody gives you the metric, you can crank the handle, you can write down this equation. But I don't want to, yeah. Sorry. Yes, thank you. It's just a trace. Thank you. It's not quadratic in R. That's right. There are other things like called the Kretschmann scalar, which are actually this convection. Thanks. Good. So you can write down the solution, but what is more interesting is the properties of the solution. So I will end on those points. I want to tell you. So such a solution then was found by Karl Schwarzschild in 1915. A few months after the publication of Einstein's paper on these equations, and I think Einstein at least communicated, he didn't write in his paper, but he made it clear that he thought that those equations, those PDEs are so hard that no one will ever find it. So when I derive these laws, by the way, I will write down the solution. We will need to write down the solution. So that's for those who want to know about it. We'll actually write down what the solution is. But now I just want to give you some physical idea of what it is. Okay, so because those solutions, they are extremely weird And in fact, until the 70s or 60s, when Penrose and Hawking and so on came along, actually most people kind of tended to discount them as saying that they are so weird. Yes, they are mathematical solutions, simple mathematical solutions of this theory, but clearly there must be some physical principle which forbids their realization in nature. So that's really true. Historically, even in history of science, this is true. People did not believe in the existence of black holes for a very long time. And it was really the achievement of Penrose and Hawking to show that they are totally inevitable and that they most likely exist in the universe. And famously now, recently, this was, I think, sort of the clinching, the nail in the, or let's say the linchpin of those who claimed that they don't exist was basically these observations by LIGO. But okay, that's a different part of the story. But so if you say, so these solutions, they basically have the property that there is a surface in space-time. It's actually the surface of a sphere, but let us zoom in onto the sphere, okay? And let's say then a two-dimensional sphere, right? If I zoom into it, it's like a plane. Locally, it's like a plane. And let's pretend that this plane is that plane that comes out of the blackboard. So this is the projection onto the blackboard of that plane. Then I will say that if we go far out to the right, we're far away from the black hole, and this can be parameterized by saying some radius goes to infinity. This thing here is what people in honor of Karl Schwarzschild call the Schwarzschild radius, and will be the location of the horizon. And if you go towards r is equal to 0, what you find is this famous singularity, which is another reason why people did not like taking black holes seriously for a very long time. So I can say a bit more about this bit. I first want to talk about the horizon, but yeah. Yeah. It's a static solution. It's static. Yes. That solution, that dimension is not correct. Correct. So it's spherically symmetric and static, and that's actually important. Okay. So now, however, I can still think about, for example, what happens to an observer who moves in this space-time. Okay. So I can ask, for example, what happens to let's say an astronaut on a rocket that like falls into this black hole. Okay, so this might be now the world line of some rocket. Maybe, you know, I don't know where you stand on this, but some people might say it'd be a good thing for Elon Musk to actually. But the point is that nothing can go faster than the speed of light. So a good thing to do is to think about the fate of light cones. So I can draw light cones, for example, in this region, and the light cones will look like this. So I can go in a direction that leads me away from the black hole, but I also have the choice to go in a direction that would lead me into the black hole. Here I can still decide. If I approach the solution, the form space and time in such a way that these light cones start tipping over. So for example, here, here the light cone will already be tipping in this direction. And there exists now a surface, which is the horizon, where light can just graze along the horizon. It's marginally trapped. It can no longer, there's no longer a causal path that leads from here to far away. Why is that? Because, you know, if I want to be causal, I have to be inside the future light cone. I have to go at the speed of light or slower. So I can go at the speed of light, I will just graze along the horizon. If I go slower than the speed of light, I'm forced to go in a direction that's inside of the black hole. And once I'm inside the black hole, now my light cones are tipped over in such a way that everywhere in my future is the singularity. Okay, so there is no causal path anymore, no way to go at a speed that is at most the speed of light, which will take me from this region to the region far away of the black hole. So here, in this region, I can escape to infinity. This region, I cannot escape. Okay, but this is a very fundamental portion of not being able to escape. There is right, because I emphasize it many times, but probably it takes some time to get one's head around it. These Einstein's equations that define both time and space are an output of Einstein's equations, and they can be deformed in interesting ways. And around the spherically symmetric solution, they're deformed in precisely this way that there exists a surface which delimits a region from which there is no causal path that does not end in the singularity. So all I can do is I can fall into the black hole and disappear in the singularity. I'll say a couple more words about this. But outside, I still have the choice. I can either fire my rocket such that I escape to infinity, or I can do nothing and be attracted into the black hole, or I can even accelerate being sucked into the black hole. But once I'm inside, there is no actual way of getting ever out again because of the very structure of space-time itself, okay? And the principle that nothing can move faster than light. And so the horizon, the surface, this horizon is just the surface that delimits the two different behaviors. One region of space-time I can get away from the singularity. The other region of space-time I can never get away from the singularity. And now let's just end on this thing. Singularity is basically is in the Schwarzschild solution. It is actually r goes to 0 in Schwarzschild coordinates, and it is such that the curvature goes to infinity. So for example, and now I can use Ruth's, what she corrected me. So if I look, for example, at the curvature mu nu rho sigma, this is a good notion of gauge invariant notion of how strong is the curvature. And this guy, I could call it k squared for the Kretschmann scalar squared. And this thing actually goes, r goes to 0. R goes to 0 is very important. I apologize. R goes to infinity, you're very far away from the black hole. R is equal to 0, you're in deep trouble. So R goes to 0, and we have that k squared goes to infinity, which implies many other nasty things, namely that, for example, the gravitational forces that you feel go to infinity, the tidal forces that you experience go to infinity. Tidal forces meaning the difference, for example, between the gravitational attraction of my right leg and my left leg. So it literally tears apart physically everything that goes there. And so this singularity is something that people don't like, and that's, understanding singularities is another goal of quantum gravity. But for now, let's stay with the properties of the horizon. And the statement is that this horizon, okay, the horizon of the Schwarzschild black hole is a sphere, it's spherical, okay? So the spatial part of it is a two-sphere in 4 dimensions, it's an S2. And as I was saying, then we should think of the Dickinson-Hawking entropy is associated to this strange surface in space-time. It's the area of this sphere that is located at the Schwarzschild radius, okay, divided by 4g Newton. And that's one of the great puzzles. One would like to understand, why should this be the case? Okay, this surface is otherwise in no other way remarkable. But I want to stop here because I've already said a lot of things. I want to give some time to prepare for the next lecture for you, and also maybe there's some questions. Thank you. Yeah. Yeah. Uh, yes, yes. Well, what is disturbing about the singularity here is that in Newtonian physics, so one way of saying it is in Newtonian physics doesn't determine, for example, what time is. So in the presence of the singularity, you don't even have any more definition of time. I mean, just everything stops. There is no arena anymore to do physics. I mean, it is in some sense this difference between, the Cartesian way of thinking that space and time are absolute. You can put an electron there. Maybe indeed there is a delta function singularity of the electron, but it doesn't mean that the arena of physics ceases to exist. Here, literally, like the arena of physics ceases to exist. There are other ways, which again, maybe in the afternoon discussion we can go into. Actually, these singularities also pose problems for actually thinking of general relativity as a causal theory, meaning that the future is determined by initial data in a sensible way. But for this, I would need to in a little bit more how you actually think about GR as an value problem, which I did not go into at all. But yeah. Other questions? Yes. Ah, extremely fast because the temperature goes like over the mass. So the smaller an object, the faster it evaporates. Good. So I think the question that you're posing is why is an electron a black hole that has already evaporated into Hawking radiation? Yeah. No, let me think about a good answer to this. Obviously, I mean, in the end, we somehow don't take into account really the delta function mass. I mean, we think of the electron as having essentially a finite extent, and that is outside of its own Schwarzschild radius. But I think we should plug into these numbers. I think probably at some point, yeah, they gave us this problem even in grad school, but we can work it out. Okay.